Hello everyone. The title of this video is Section 4.4 Part 1 on solving systems of linear equations in 3 variables. So in this video I'm going to be going over a version of the Knewton Alta homework for this Section 4.4 Part 1. Please know that the version I'm looking at, the questions I'm going to be doing in this video, are not necessarily going to be the exact same questions you'll see when you work on Section 4.4 Part 1's homework. But the objectives will be the same, and the types of questions will be the same. So how I go about doing them and answering them will be similar. Right? So hopefully watching me do this will help you when you work on this assignment on your own. Okay. So here's a page with the assignment. You will not be seeing the word preview. Right? What you will see is just the title of the section and the mastery bar telling you how far along you've gotten. The objectives here. This section has 3 objectives. Question below on a particular objective where you enter your answers. There's a feedback box that you can send feedback to Knewton if you wish. You will not see the instructor cheat button. Right? You won't see this. And then you'll have a more instruction button, right, which you click on that when you're struggling with a question or an objective, and it'll give you some reading material or maybe a video that'll hopefully help you, when you're working on the problems. All right, so this first question is on the objective: solve a system of linear equations with 3 variables. So in this section, we're going to be given systems of equations, right? 3 equations, and throughout these 3 equations, we'll see 3 variables appear, right? X, and they'll be typically x, y, and z. Right? And what we're trying to do is find a value of x, a value of y, and a value of z that solve the system, that satisfy all 3 equations at the same time, right? Not just 1 or 2 of them, but all 3. And the way we'll enter our answer at the end is, it's what they call an ordered triple, right? Because there are 3 values, not an ordered pair. And the first value will be the x, the second value will be the y, and the third value will be the z. Right, so I'm going to write out this system and talk about how to solve a system with 3 equations and 3 variables by elimination. Alright, so here's the system. Again, we have 3 equations with 3 variables, x, y, and z, showing up. And we're asked to solve by elimination. Now, I'm hoping you've seen elimination when there were 2 equations and 2 variables, right, like just x and y. Because the elimination method for a 3 equation, 3 variable system is pretty much the same steps, but things are repeated more often. Right, and you'll see what I mean hopefully here. Alright, so I'm going to label these equations just because I don't want to keep writing them out all the time. So this will be equation 1, which I'll just call E1. This second equation will be equation 2, which I'll just call E2 for equation 2. And the third equation I will call equation 3, right, or E3. Right, so if I ever refer to E1, E2, E3, I'm referring to these 3 equations. Alright. So the first step is to pick a variable to eliminate. Now, with experience, with more practice, you'll notice that some variables in certain scenarios will be easier to eliminate than other variables. So having looked at this, I feel like it's going to be easiest to eliminate x's. So I'm going to choose to eliminate x. eliminate x's. Now, what you're going to do is you're going to do this twice. You do this with two pairs of equations. So that's all I meant earlier by how this is going to be a bit more repetitive. Alright, so the first time is going to be with equation 1. I'll just take equation 1 and 2. Right, equation 1 and equation 2. Now for this first example, I'll do a lot of writing out. So we have, negative 5x plus 5y plus 5z equals negative 15. Equation 2 is, x minus 4y minus 2z equals 12. Now remember how to eliminate a variable when you have two equations. You've done this before. I want to eliminate, I have chosen to eliminate x's. The first equation here has negative 5x. And I could easily get the coefficients to be opposites if I just multiply the second equation multiply the second equation by positive 5. Then I'll have negative 5x, positive 5x, and then I'll add the equations and eliminate x. So if I multiply by positive 5, here's what I'll get next. So the first equation, I'm not changing. Negative 5x plus 5y plus 5z equals negative 15. The second equation, I'm multiplying everything by 5. So you have 5x minus 20y minus 10z equals 60. And now that the coefficients of the x's are opposites, positive 5, negative 5, I will then add the equations together to create a new equation. So I'm lining up equal signs here, combining all the like terms on the left, combining the terms on the right. And you see that the x's will be gone. Negative 5x plus 5x is nothing. Positive 5y plus negative 20y would be negative 15y. 5z minus 10z would be minus 5z equals, and then negative 15 plus 60 would be positive 45. All right. So I've eliminated x, and look at this. I'm left with an equation. If I eliminate x, I'll have an equation with the other two variables, right? An equation with y and z. And one thing I noticed about all these coefficients, negative 15, negative 5, 45 on the other side, they're all multiples of 5, so I'm going to do this. I'm going to divide everything by 5. Let's put division by 5 and create this new equation where we have negative 3y minus z equals 9. All right, so this equation, now this isn't the answer, I'm just putting it in a bubble. I will call this equation equation 4. E4. Right. And notice that it has y and z, two variables instead of 3. So if I do this again, right, if I eliminate x again with another pair of equations, right, instead of equation 1 and 2, how about equation 1 and 3 or 2 and 3? If I do it again, then I'll have a second equation with y and z. And what we'll have done is taken 3 equations with 3 variables, eliminated one of them twice, and then we get 2 equations with 2 variables. And you know how to solve 2 equations with 2 variables. Right? You solve for those 2 variables, and then you're going to go back and solve for the third one. Right? All right, so let's do that again. So I eliminated x from equation 1 and equation 2 here. Second time, let's take this time again. Look at equation 1 and 3. They already have opposite x coefficients, right? I still want to eliminate x, so those will be really easy. So let me do it with equation 1 and equation 3. So equation 1, right, negative 5x plus 5y plus 5z equals negative 15. Equation 3, 5x plus 6y minus 3z equals negative 13. Now the coefficients of x's are already opposites, so I can add the equations right now and get a new equation with just y and z. So the x's will be gone. I'll have 11y plus 2z, right, 5 plus negative 3, equals, and then negative 28. Alright, so again, this isn't the answer, just putting it in a bubble. I'll call this equation 5, right, E5. And notice that equations 4 and 5, right, E4 and E5, right, these two equations I got after eliminating x from two different pairs of the original equations, E4 and E5 make a system of two variables, right? Make a linear system with two variables, right? Y and z. Both of these equations have y and z. And you should know how to solve such a system. So you solve this system for y and z, and then you go back and use your values of y and z and solve for x back in one of the original equations, and I'll show you that now. Alright, so here we go. All right, here's this new system. So again, equations 4 and equation 5. We have the following system, right? Negative 3y minus z equals 9, right? That's what I got from that first elimination of x. Then 11y plus 2z equals negative 28, right? That's what I got from the second elimination of x. So now there's no x's, and then you kind of start over, right? I've said this out loud, but we're going to solve this system of two variables. Solve for y and z. Alright, well, I think the easiest of the two variables to eliminate would be the z's. I've got positive 2z in the second in equation 5 here. I could multiply the equation 4, multiply equation 4 by 2, and then we'll have negative 2z, right? So negative 2z, positive 2z, they'll be opposites. So after multiplying equation 4 by 2, we'll have the following system. That would be negative 6y minus 2z equals 18. The second equation I'm not touching, we're not doing anything. You could say times 1. It's 11y plus 2z equals negative 28. And now that the coefficients of z's are opposites, negative 2 and positive 2, we add to make a new equation. And that'll eliminate the z's, and I'll be left with y's. Negative 6 plus 11 is 5y on the left equals 18 plus negative 28 would be negative 10 on the right. And I solve for y, right? Divide by 5, y equals negative 2. Here is the y value of the solution of this system. But that's only 1/3 of the solution. Remember, we need a value of x and a value of z at the very end. But now that I have this value of y, I can go back into this system with y and z and solve for z. So let's go back to, say, equation 4. All right, we have negative 3y minus z equals 9. And replace y with negative 2. Right, replace y with negative 2. So that'll be negative 3 times negative 2 minus z equals 9. So we have 6 minus z equals 9. Z would have to be negative 3. Right? Subtract 6, divide by negative 1. There's the z value of the solution. And now I'm 2/3 of the way done. Right, I've got the y coordinate, the z coordinate. Now we need the x. So now I go back, go back to the original system, and I'm going to replace y with -2 and z with -3 in any of these equations with x in it and solve for x. So now let me just go back to equation 2 here. Equation 2 will be easy because it's just got 1x. So if I go back to equation 2, we'll have x, then minus 4y, so minus 4 times -2, then minus 2z, so minus 2 times -3 for z, equals 12, right? And we solve this for x. Well, this will be x, and then we have plus 8 plus 6, that's x plus 14 equals 12. X must be -2 if I subtract 14. Alright, so the solution of this system, again, it's going to be an ordered triple, right? An ordered triple. There are 3 values, an x value, a y value, and a z value. Alright, and this is the x coordinate we saw was -2, comma, the y coordinate also -2, comma, and the z value for the solution -3. And I'll put this in a little circle. This is the solution of the system. Now don't forget to check. Don't forget to check your solution. Let's go back to the original system. All right, there's equations 1, 2, and 3. If I were to replace x with -2, y with -2, and z with -3, if I did everything correctly, all 3 equations should be satisfied. I'm going to do that out loud. All right, if x were -2 and y were -2 and z were -3, we'd have 10 minus 10 would be 0, and then plus -15 would be -15. The first equation would be true. Second equation, we'd have -2 plus 8 is 6, plus 6 would be 12. That's true. That's also true, the second equation. In the third equation, you'd have -10 plus -12 would be -22 plus 9. -22 plus 9 would be -13. This satisfies all 3 equations, so it is indeed a solution of the system. And that's what we're going to enter. We're just going to be entering the x coordinate, y coordinate, and z coordinate. And again, be careful. They already have the parentheses and the commas here. So don't type the parentheses or the commas. You're just entering the x value, which was -2, in the first box. That second middle box, you're putting the y value, which was also -2, and the z value of the solution in the third box, that final right box, -3, and then submitting. Correct, hooray. Now please read through the answer explanations. All right. Now, for some reason, they decided to eliminate the z's. I chose to eliminate x's. Whatever, right? And you see how, again, they eliminated z twice, giving you 2 equations with x and y. And then you solved that system of 2 equations with x and y. You solved that for x and y, and then went back to one of the original equations and solved for z. You get the same result. But you will have these answer explanations after every question, right? Whether you get it right or wrong. Now, if you get it right and you are still unsure about some things, read through the answer explanation. See if what you wrote down makes sense compared to what they wrote down. Maybe you got lucky, and you don't want to get right because you were lucky. You want to get right because you want to get things right because you know what you're doing. And then, of course, if you get it wrong, read through the answer explanations to see if you can figure out where you went wrong. And then hopefully that'll help you do better the next time around. Alright, so next question. Alright, so this one is on a different objective. We're asked to identify inconsistent and dependent systems of equations with 3 variables. Alright, so they're asking us, basically, they're giving us a system of equations with 3 variables, and asking us, does that system have one solution, no solution, or infinitely many solutions? Now, a system with no solution, that is an inconsistent system. And a system with infinitely many solutions is a dependent system. Right? A system with one solution would be called a consistent and independent system. But again, that's not important. Right? So let's see what happens. All right, let's go through and try solving this by that elimination method I talked about in the previous example. All right. So I got three equations. Now notice that not all three equations have all three variables, which is nice. That'll actually cut down the amount of work we need to do. Once again, I'm going to call this first equation E1 for equation 1, second equation E2 for equation 2, and the third equation E3 for equation 3. Now notice that equation 2 already has just two variables. This already has just x and y. And if you recall from the last example, I want to get a system with three equations and three variables down to a system of two equations and two variables. Well, I've already got one equation with two variables, x and y, so all I need to do now to get a second equation with x and y is eliminate z using the first and third equation. Right, so I'm going to eliminate z from equations 1 and 3, right, E1 and E3, and that's it. I'm not going to have to do that twice like I did in the last example because there's already an equation with two variables. I hope that makes sense. So equation 1, x plus 3y plus 2z equals 2. Equation 3, negative x minus 2y minus z equals negative 4. And once again, I'm saying I want to eliminate the z's, so I get a second equation with x and y. Well, in order to eliminate the z's, right, there's positive 2z there. I can make this into negative 2z by multiplying the second equation, every single term on both sides, by positive 2. Alright, so that'll lead me to the following. First equation I didn't touch, right, so it's still x plus 3y plus 2z equals 2. The second equation, I'm multiplying everything by 2, so we have negative 2x minus 4y minus 2z equals negative 8. Now the coefficients of the z's are opposites, so when I add the sides together to make a new equation, the z's will be eliminated. And I'll have negative 1x minus 1y equals negative 6. Alright, in this equation, again, I'm putting it in a bubble, but this is not the answer. This is just a new equation. I'm going to call this equation, equation 4. Say E4. Now notice that E2 and E4 just have x and y. So if you look at E2 and E4, what you're getting is a system of equations with just two variables. Right? Equation 2 is negative 2x minus 2y equals negative 12. Equation 4 here is negative x minus y equals negative 6. And now I'm going to solve this system. Right? Solve this system for x and y if I can. And if this has a solution in x and y, then I can go back to one of the original equations, right, equation 1 or equation 3 that has z in it, and solve for z. Well, we can do some simple elimination here. If I want to eliminate the x's, say, I would just have to multiply the second equation by negative 2. Right? So that'll give me negative 2x there, positive 2x there. So in doing so, first equation, equation 2 I didn't touch. Negative 2x minus 2y equals negative 12. And then equation 4 here, multiplying by negative 2, that's positive 2x, and then positive 2y equals positive 12. And look at this. What happens when I add the equations here? Both terms, the x's and y's, will be eliminated on the left, so I'll have 0 on the left. Same thing on the right. Negative 12 plus 12 is 0. If this ever happens, and again, you've probably come across scenarios like this in equation solving, but if this ever happens, you're trying to solve something with variables, and then the variables are eliminated somehow, and you end up with a completely true statement, right? 0 equals 0 is true all the time. That is always true, no matter what variable values you're using. If that is the case, right, if you try solving a system and you end up with 0 equals 0, or 1 equals 1, 2 equals 2, right, something that's clearly a true statement with no variables, that tells you that the system has infinitely many solutions. Okay, this system, there are infinitely many values of x and y and z that you could use that would satisfy all three equations. All right. And I put a different video besides this where I went into actually how would you find such values, but we're not asked that here. All right, so I'm going to stop. Just say, hey, 0 equals 0. That's a true statement no matter what. Variables are gone. All right, this has infinitely many solutions. And if a system has infinitely many solutions, that system would be called a dependent system, or a consistent system with dependent equations, but the word dependent will be used. All right. So that's what I'm going to enter. That's what I'm going to toggle back here. This system has infinitely many solutions. Now, you'll have no solution if you end up with a statement like 0 equals 1, right? So, where all the variables are gone, but the statement you're looking at is clearly false, right? 0 equals 1, 1 equals 2, 3 equals 5, And then if you have one solution, well, that'll be just like the first example, where you'll actually find a value of x, a value of y, a value of z that satisfy all three equations. Okay. So again, please read through the answer explanations. Cool. All right, next question. So we're back to the same objective here, identify inconsistent dependent systems of equations with three variables. So it's again asking me, does this system I'm looking at have one solution, no solution, or infinitely many solutions? All right, so I'm going to again write out the system on paper and we'll work on it. All right, so again, now notice what I've done. All right, this isn't the way it looked on the computer, on the Knewton's site. I've again, and you've seen me do this with examples with systems with two equations and two variables. I want to do the same thing for three equations and three variables. I get all the terms with the variables to one side of the equal signs and all the constants to the other side. And then I like to set it up, I like to write them so that all the like terms are lined up, right? The x terms are in one column, the y terms in another column, and the z terms are lined up in another column. All right, now you may notice that not all three equations have all three variables. The first equation has just x and z. The second equation has just x and y. The third equation has just y and z. So just pick one of these. All right, I'm going to pick the first equation. I'm going to keep that one. So I'm going to notice that the first equation has just x and z. All right, it already has only two variables. And then what I want to do now is create another equation with x and z. And then I'll have a system with two equations with x and z, two equations and two variables that I can solve. So if I'm keeping the first equation with x and z, that means I want to eliminate y from equations 2 and 3. Right, if I eliminate the y's from equations 2 and 3, that'll create another equation with just x and z. Alright, so equation 2, that's negative 6x plus 4y equals negative 28. And then equation 3, negative 2y plus 3z equals 5. And once again, I'm saying I want to eliminate the y's. Well, that'd be pretty easy to do. All I need to do is multiply equation 3 here, this equation, by 2. If I multiply everything by 2, then I'll have negative 4y here, positive 4y there, and then we can add the equations to eliminate y. Alright, so after multiplying that equation by 2, this top equation stays the same, negative 6x plus 4y equals negative 28. And this bottom equation becomes negative 4y plus 6z equals 10. Now the coefficients of y's are opposites, so when I add the equations together to create a new equation, the y's are eliminated, and I have negative 6x left, y's are gone, plus 6z equals negative 18. Negative 28 plus 10. Right, and this I'm going to call equation 4, E4. And notice that equation 1 and equation 4 now form a system with two equations and two variables. So look at equation 1 and what I'm calling equation 4, and we get the following system with just x and z. Now equation 1 is 4x minus 4z equals 12, and this equation I got here after eliminating the y's from equations 2 and 3, negative 6x plus 6z equals negative 18. Alright, you know what? I'll actually rewrite this. Something I'm noticing about the coefficients in this equation is that they're all multiples of 3, so what I'm going to do is I'm going to divide everything by 3. And that'll make this equation, I'm sorry, 6. They're all multiples of 6, my bad. Divide everything by 6. And that'll just give me negative x plus z equals negative 3. Let's use that instead. Right, so I'm going to scratch this off. Sorry about this. And I'm going to use negative x plus z equals negative 3 instead. Now you might see it already. This is kind of like the last example where the first equation is just negative 4 times the second equation. They're the same equation, so every solution to the first is going to be a solution to the second. This is going to have infinitely many solutions, but let's continue on and finish it off. So say I wanted to eliminate x. Multiply the second equation by 4, and that gives me the following setup. So we have a 4x minus 4z equals 12 on top. Multiplying the second equation by 4 gives me negative 4x plus 4z equals negative 12 on the bottom. We have the coefficients of x's are opposites, and so are z's. Right? So when I add these, you'll have 0 on the left, and 12 plus negative 12 is 0 on the right. And then this is just like the last example. Alright, if you're trying to solve an equation, if you're trying to solve a system of equations, and you end up getting rid of the variables, and you're left with a completely true statement with no variables, right? This is 0 equals 0, 1 equals 1, 5 equals 5, whatever. That again means that the system has infinitely many solutions. Alright, and this is what I'm going to toggle back on the problem. Right. And once again, if you ever come up with a statement that's not true with no variables, 0 equals 2, 1 equals 5, that just tells you that the system has no solution. Be aware of that. That may come up. But yeah, so this is another system that has infinitely many solutions. All right. All right, next question. All right, so now we're into a pretty easy one. All right. You're given a system with 3 equations, and there are 3 variables involved. And all you're asked to do is determine whether an ordered triple is a solution of a system. Right. Now, if you recall, right, an ordered pair, an ordered triple, whatever ordered tuple you're looking at, it's a solution of the system only if it satisfies every single equation. Right? It can't just satisfy the first one and the third one, but not the second one. Right? It can't just satisfy the second one, but not the first one, and so on. You have to be a solution to all 3 equations. Right? So again, this should be the easiest of the objectives. Just plugging in and checking. All right, so once again, here's the system we were given, and the ordered triple we're given is -1, 3, -3. And don't forget, this is, -1 is the x value, 3 is the y value, and -3 is the z value. So what I'm doing here is I'm just going to go through each equation, and I'll call them equation 1, equation 2, and equation 3. I'm going to go through each equation and see, does this ordered triple, do these values of x, y, and z satisfy each equation, make each one true? Alright, so equation 1, we have 4 times the y, so 4 times 3, plus 5 times the z, which is -3. 5 times -3. Is this equal to -3? Well, this left side would be 12 plus -15, that is -3. So we get -3 equals -3. That is true. Great. Again, that doesn't mean anything, though. Right? That doesn't mean that this is a solution of the system. It's just a solution of the first equation. Right? It has to be a solution to all 3 equations to be a solution of the system. All right, equation 2. We got y on the left, so 3 equals -1 times x, so -1 times, the opposite of -1, that'll become +1, and then plus 2. Let's see, we have 3 on the left equals 1 plus 2 is 3 on the right. Also true. Fantastic. So far so good. This ordered triple is a solution of the first 2 equations, but again, that doesn't mean it's a solution of the system. Has to be satisfying all 3. So now I'm going to equation 3. Left side we have 4 times the x, so 4 times -1, minus 3 times the z, so -3 times -3, right, equals 5. This is -4, this is +9. -4 plus 9 would be 5. We have 5 equals 5, which is also true. This ordered pair, ordered triple, this satisfies all 3 equations, every equation in the system. So this is a solution of the system. So the answer back on the page is yes, right? Yes, it does. It satisfies the following system of equations. Right. And again, please read through the answer explanations. Okay, next question. Alright, so the same objective again, right? Again, this should be one of the easier ones. Right? It's just determining whether an ordered triple is a solution of a system of 3 equations with 3 variables. So I'm going to write this system out, and we'll test that ordered triple. Okay, so here's the system we're given, and we're asked, is the following ordered triple, -2 for the x, 0 for the y, and -5 for the z, right? And then again, remember that's x, y, z. is that satisfying all the equations in the system? Right. All right, so once again, I'll call the top equation equation E1, E2, and then E3 for the equation 1, 2, and 3. And let's test it out, right? So in equation 1, we have y minus z equals 5. So the y coordinate, which is 0, minus the z, which is negative 5, is this equal to 5? Well, yeah. 0 minus negative 5 would be 0 plus 5. We'd have 5 equals 5. True. I'll just put a check mark for true. So far, so good. Right. Now I can move to equation 2. As soon as one of these fails, you stop, right, and say, no, it's not a solution of the system. All right, so we have negative 4 times x, so negative 4 times negative 2, minus 4 times y, so minus 4 times 0, plus z plus negative 5, and is this equal to 3? All right, this is positive 8 minus 0, so still 8. 8 plus negative 5 is 3. We have 3 equals 3. Wonderful, that's also true. All right, equation 3. We have negative 3 times x. Right, so negative 3 times negative 2, plus the y, which is 0, plus 2 times z, 2 times negative 5. And is this equal to negative 4? Yeah, we have 6 plus 0 is still 6, plus negative 10. 6 plus negative 10 is negative 4. So I have negative 4 equals negative 4. Once again, all three are satisfied. Every equation is satisfied, so this is a solution. So I'll say yes, right? Yes, this ordered triple is a solution of this system, because all the equations are satisfied. And once again, as soon as you find one equation that is not true, then the ordered triple is not a solution, right? But that didn't happen here. So once again, the answer is yes. All right. Next question. So here we're back to doing it ourselves. Right? We're asked to find the ordered triple, the x, y, and z that satisfy all three using this elimination method. And notice that the equations are already set up nicely. I have the x's and y's and z terms all lined up on the left side, and then the equal signs, and then all the constants on the other side. So this is already set up in a nice fashion to make the elimination method easier. All right. So this system here is like the system we saw back in the first question from this video. All three equations have all three variables. So when I choose to eliminate a variable, I need to do it twice. All right. So one more time here, I feel like x is going to be easy to eliminate. You choose whatever variable you wish, but I'm going to choose to eliminate the x's, and that'll leave me with equations with y and z. Right? And again, I want to do this twice so that I have two equations with y and z, and then I'll solve that system of two equations for y and z, and then go back to one of the original equations and solve for x. So first I'll do it from equations 1 and 2. All right, so we have equation 1, x minus 6y minus 2z equals 7. Then equation 2, negative 2x plus 5y minus 2z equals negative 1. All right, now again, I'm choosing to eliminate the x's here, so all I would need to do that would be multiply the top equation by 2. That'll give me 2x and negative 2x. Right? So after multiplying the top equation by 2, I got the following. 2x minus 12y minus 4z equals 14. And the second equation I didn't touch, so it's still negative 2x plus 5y minus 2z equals negative 1. Now the equations have opposite coefficients on the x's, so I can add to eliminate x. So on the left side, I'd have negative 7y minus 6z, combining like terms, and then equals 13. All right, and I'm going to call this equation 4, E4. Right? And notice now that it's an equation with just y and z. And I'm going to do this again. I'm going to eliminate x again with a different pair of equations from the original system. And that'll give me a second equation with y and z. And then I'll have a system of two equations with y and z. So this time I'll do equation 1 and 3. Right? Again, you can do equation 1 and 3 or equation 2 and 3, whatever you want, just so long as you're eliminating the same variable again. So equation 1, x minus 6y minus 2z equals 7. Equation 3 is negative 5x plus 6y plus 5z equals negative 6. And then again, I'm eliminating x, so I get another equation with y and z. Easy to do here, just multiply the top equation, every term, both sides, by 5. And that'll give me 5x and negative 5x. And so if I do that, the top equation becomes 5x minus 30y minus 10z equals 35. Second equation, the bottom equation, sorry, the third equation 3, stays the same. I didn't do anything to it. Negative 5x plus 6y plus 5z equals negative 6. Right, now that the coefficients of the x's are the same, we can add and eliminate x. So the x's will be gone. I'll have negative 24y minus 5z equals 29. All right, great. And I'll call this equation with y and z equation 5. So look at equations 4 and 5. These have just y and z. Right? So, and you should be able to solve a system with just two variables. So looking at now equations 4 and 5, we have this system. Negative 7y minus 6z equals 13. And then the other one, negative 24y minus 5z equals 29. Right. Okay, now looking at these two, I feel like the smaller numbers, the smaller magnitude numbers, are on the z's. So I'm going to eliminate z. Now the least common multiple of 6 and 5 is 30. So to eliminate z here, I would have to multiply the top equation by 5. That'll give me negative 30z. And then I would want positive 30z in the bottom, so I multiply by negative 6. Right, so I multiply the top equation by 5 and the bottom equation by negative 6. So top equation by 5, we have negative 35y minus 30z equals 65. Bottom equation by negative 6. All right, negative 6. Negative 6 times negative 24 would be positive 144. Right, 120 and 24. 144y plus 30z equals, and then negative, and then let's see, 173, right? 120 and 63. Or, I'm sorry, no, 174, 120 and 54. Duh. All right, so negative 174. Now that the coefficients of z's are opposites, we add to eliminate z. And 144 plus negative 35, 144 minus 35, that'd be 109. All right, 109y equals, and then the z's are gone. Then this would be negative 109, wouldn't it? Yeah. negative 109. So look how nice this turns out, even though all the numbers are getting kind of big. Dividing by 109 gives me the value of y for our solution. Y equals negative 1. Alright, so now I have the y value. I can go back to either one of these equations, equation 4 or 5, and solve for z. So I'm going to go back to equation 5. We have negative 24 times y, so negative 24 times negative 1 minus 5z equals 29, and I solve for z. Well, this is 24 minus 5z equals 29, so hopefully you can see that z would also have to be negative 1. So the y value and the z value, I would subtract 24 divided by negative 5, right? Y value and z value would have to be negative 1, but now, right, that's only 2/3 of the answer. I need to find the x value of the solution. So we go back. I'm just going to go all the way back to equation 1 because it has 1x. That'd be easy to solve for x. So I go back to equation 1, and I'm going to substitute negative 1 for y and negative 1 for z and solve for x. So we have x minus 6 times the y, which is negative 1, minus 2 times the z, which we have found is negative 1 as well, and this is equal to 7. So this is x plus 6 plus 2, that's x plus 8 equals 7, and oh, look at this, wow. X would also be negative 1. So the solution of this system is the ordered triple, negative 1 for x, comma, negative 1 for y, comma, negative 1 for z. And test it out, right? Test it out. Take this ordered triple, go back to the original system, right? This equation 1, 2, and 3. Replace x with negative 1, y with negative 1, and z with negative 1, right? And we're checking here. Well, let's see, we'd have negative 1 plus 6 is 5, plus 2 is 7, that's true. 2 minus 5 is negative 3, plus 2 is negative 1, that's true. 5 minus 6 is negative 1, minus 5 is negative 6, that's also true. This ordered triple works for all three equations. And so that's what I'll enter back in the assignment. Right. Again, they already put the parentheses and the commas. You're just putting the x coordinate, y coordinate, and z coordinate. So negative 1 for all three. Right? I'm just typing in negative 1 in all three of these boxes and then submit. Fantastic. And again, please read through the answer explanations. Now look, they chose to eliminate the z's first. I eliminated x's, but you end up with the same result at the end as long as you're doing things properly. All right. Next question. All right, so this is another one of those easier ones, right, where you're just replacing x, y, and z with some value and seeing if all the equations in the system are true. All right. So once again, I've written out the system, equation 1, equation 2, equation 3, and the ordered triple, sorry, I almost said pair, the ordered triple, the x, y, and z values we're asked to test are 0 for x, comma, negative 4 for y, comma, and 0 for z. And we're asked to see if this ordered triple is a solution of the system. Does it satisfy all three equations? Alright, so let's look at equation 1. So we have 3 times x, right? 3 times 0, minus 2 times the y, being minus 2 times negative 4, plus 4 times z, 4 times 0 again. Is this equal to negative 4? Well, no. This is 0, this is 8, this is 0, so adding all that up, that's 8 on the left. And then you got negative 4 on the right. 8 is not equal to negative 4. This is false. And I can stop. As soon as you find an equation that the ordered triple doesn't satisfy, then you know that this ordered triple is not a solution of the system. It might be a solution of one of these equations, but it's not a solution of all three. Right? And you can stop as soon as you find one. So this is not a solution of the system. Or to answer their question, just simply say no. It's just a yes or no question. Right. Great. And it actually doesn't satisfy any of them. But again, as soon as you find one equation it doesn't satisfy, then you don't have a solution to the system. All right, next question. All right, looks like the final question I'm going to get on this objective, as long as I get it right. Don't forget, don't guess on things, right? If you get something wrong, it's going to back the progress bar up a bit, and then you'll have to do more. So I'm going to write this system out, and we'll test that order triple. Okay, so here again is the system they gave us: equation 1, equation 2, equation 3 from top to bottom. And the ordered triple we are given to test is -8 as the x coordinate, -5 as the y, and +6 as the z. Right? So I'm replacing x with the y and z with these three values respectively, and seeing if all three equations are made true or not. Right, so in equation 1, we have -3 times the y coordinate, so -5, -2 times the z, which is 6. Is this equal to +3? Well, this would be 15 minus 12, that's 3, and we have 3 equals 3, great. So far so good. The first equation is satisfied. Equation 2. We have -x, so the opposite of -8. -1 times -8, that'll be +8 eventually. Plus y, right, so plus -5. Is this equal to 3? Well, that's 8 plus -5, that is indeed 3. We get 3 equals 3 again. Check on that. So far, so good. Now, equation 3. 3 times x, so 3 times -8. -3 times y, -3 times -5. Plus 2z, so plus 2 times 6. Is this equal to 3? No. This is -24 plus 15. That would be -9. Then plus 12. Oh, nope, that would be 3. I'm sorry. That is 3. So yeah, -24 plus 15 would be -9. Plus 12 would be +3. Yeah, so this is 3 equals 3. This also works. Great, so the answer to their question is yes, right? This is indeed a solution of that system. Satisfies all the equations. All right, so that objective's done. Still got the other two to complete. So next question is on the objective of just solving a system, right, through this elimination method. Now again, you'll notice that, well, they don't write it out as nicely as I'm going to, but notice that when we're asked to solve ourselves, they put all the variables on one side, constants on the other, which is what I would ask you to do normally. All right, so if it's not like that and you're asked to solve a system, that's a good first step. Put all the variable terms to one side, constants on the other. All right, so again, I'm going to write this out, and I'm going to write it out in a nice way where all the variable terms, all the like terms are lined up in columns. All right, so here's the system they have for us. Again, I wrote them so all the x's were in a column, all the y's are nice and lined up, all the z terms are nice and lined up, the equal signs, and the constants. All right, and I would recommend you do this to start as well when solving a system of linear equations. Alright, so again, I'm going to call from top to bottom here, equation 1, equation 2, and equation 3, E1, E2, E3. Now you'll notice that this is pretty nice. This will cut, there's less work to do with this one. The first equation has just x and z. The second equation has just x and y. The third equation has just y and z. So I'm going to keep one of these equations the way they are, and then eliminate a variable from the other two. Because, each of these equations already only has two variables. So I am going to keep, equation, equation 3. And again, pick what, you could keep whatever one you want. But I'm going to keep this. This has, variables y and z only. Alright, so what I'm going to do now is in equations 1 and 2, I'm going to eliminate x's. And that'll give me a second equation with y and z. And then I'll use equation 3 and that other equation with y and z and solve that system with y and z, solve for y and z, go back and solve for x. So I'm going to eliminate the x's from equations 1 and 2, right, since I'm keeping equation 3. So equation 1, negative 3x plus 6z equals negative 3. Equation 2 is 6x plus 5y equals negative 3. And it would be pretty easy to do elimination of x here, and that's why I chose equation 3 to keep. Multiply the top equation by 2. Right, both sides, every single term. Because if I do that, I'll have negative 6x there and positive 6x in the second equation there, so it'll make elimination easy. So first equation, top times 2, you have negative 6x plus 12z equals negative 6. Second equation I didn't touch, so it's 6x plus 5y equals negative 3. See, now the coefficients of the x's are equal, or opposites, sorry, negative 6 and positive 6. So now I can add the equations to make a new equation. And this new equation will have just y and z. It'll be 5y plus 12z equals negative 9. And I'm going to call this equation equation 4, right? E4. Now notice, equations 3 and 4 have just y and z in it, so they form a system of two variables, two equations and two variables, and you should know how to solve such a system. So equations 3 and 4, I have a negative y plus 5z equals negative 13. In this one you have 5y plus 12z equals negative 9. And look, you solve this system for y and z, and then go back to one of the equation 1 or 2 with x in it and solve for x. Right. Alright, so in this system, I think it would be easiest to eliminate the y's. Alright, all I would have to do is multiply the top equation by 5, because that'll give me negative 5y. And below that I have positive 5y, and when I add the equations together, those will be eliminated. Alright, so if I multiply by 5, the top equation becomes negative 5y plus 25z equals negative 65. Second equation there is 5y plus 12z equals negative 9. And then I add them up. The y's are gone. And again, I'm adding. The y's are gone. You have 37z. And then over here you have negative 74. Dividing by 37, you get z equals negative 2. Right, there's the z value of the solution. Right, and then I go back to either of these equations with y and z. Using z equals negative 2, I can solve for y. So I go back to, say, just go back to equation 3. We have negative y, negative 1 times y, plus 5 times z. Z is negative 2. That should be equal to negative 13. Right? Using, again, this equation here. And this is negative y minus 10 equals negative 13. So I'm hoping you can see that y must be 3, positive 3. Alright, so now I have z value, y value, And now I can go back to any of the original equations that have an x in it and solve for x. So it really doesn't matter. I'll go to equation 2. Why not? It doesn't matter as long as you pick one with x in it. So equation 2, you have 6x plus 5y, and the value of y is 3, so 5 times 3. And there's no z, so I don't have to worry about plugging in negative 2 for z, and that's equal to negative 3. So we have 6x plus 15 equals negative 3. Subtracting 15 would give me negative 18. Dividing by 6 would give me negative 3. So the solution of this system is the ordered triple. And again, make sure you're putting these in the correct order. Don't put them in the order that you found them. Alright, don't put negative 2, comma 3, comma negative 3. Don't do that. Make sure you're putting it in correct order with x value first. X value is negative 3, comma. Y value second, positive 3, comma. Z value last, negative 2. There's the ordered triple that solves this system. And don't forget to check before you enter your answers, right? Check your solutions. Go back to the original system and substitute negative 3 for x, 3 for y, and negative 2 for z, and see that all three equations are made true. So if I do that, we'd have 9 minus 12 is negative 3, that's true. Negative 18 plus 15 is negative 3, that's true. Negative 3 plus negative 10 is negative 13, that's true. All right, this does satisfy, these values satisfy all three equations. All right, and then that's what I'll enter back on the page here. Again, they already have the parentheses and commas. You just have to put the right things in the right boxes. So negative 3 in the x, positive 3 for the y, negative 2 for the z. Right. And submit. And again, read the answer explanations, please. All right, and then continue. I have one more question here where I'm asked to solve a system myself. So let me write that out. All right, so this one again, I'm calling from top to bottom the equations, equation 1, 2, and 3. And this time I'm going to keep I'm going to keep equation 2. All right, equation 2. I'm keeping this one, right? This has x and y already, right? Just x and y. And I want to form another equation with just x and y, which I'm not seeing yet, but we can make it easily by eliminating z from equations 1 and 3, all right, because I kept equation 2. So I'm going to eliminate z from equations 1 and 3. And this should be really easy. That's why I chose the second equation, because look at the equation 1 and 3. The coefficients of z's are already opposites. So we have 6x minus 3z equals negative 9. Then we have negative 6y plus 3z equals negative 15. And I can already just add them to eliminate z. And I'll have 6x minus 6y equals negative 24. And you might notice, hey, all these coefficients are multiples of 6. So if you'd like, we can divide both sides by 6 here just to make the numbers a bit smaller. So this would be x minus y equals negative 4. Right, and this is what I'm going to call equation 4. Now if you look at equation 2 that I kept earlier, that has x and y. Equation 4 here, right, after eliminating the z's from equation 1 and 3, that has x and y. So equation 2, what I'm calling equation 2 and equation 4, form a system of two equations with two variables that you should be able to solve. They form this system. Negative 3x plus 4y equals 14, and x minus y equals negative 4. And we're solving this system. Solve for x and y, and then I go back to one of the original equations with z and solve for z. Alright, so this one's pretty simple to eliminate one of the variables. I can eliminate y pretty easily by multiplying the second equation by 4. that'll give me negative 4y here and positive 4y there. Alright, so if I do that, right, the top equation stays the same. Negative 3x plus 4y equals 14. Second equation, I multiplied everything by 4, so we have 4x minus 4y equals negative 16. And now I can add the equations together because the coefficients of y's are opposites, and I'll have x on the left equals negative 2 on the right. There's the value of x. X equals negative 2. And then I'll just go to this equation here, just go back to equation 4, and we have x is negative 2 minus y equals negative 4. And then I'm hoping that you can see that y must be 2. Y must be positive 2. Alright, so again, add 2, divide by negative 1. So x is negative 2, y is positive 2. And then I can go to any of the equations from the top. I'll just go to equation 3. Go to equation 3. We have negative 6 times y, so negative 6 times y is 2, plus 3 times z equals negative 15. And this is negative 12 plus 3z equals negative 15, so z must be negative 1. Alright, I would add 12 divided by 3. And there we go. We have our ordered triple. Alright, so the solution of this system, x is negative 2, comma, y is positive 2, comma, z is negative 1, parentheses, right there. There's our solution. Don't forget to check it though. Let's check it out. So replace x with negative 2, y with positive 2, and z with negative 1, and see that all three equations are true. Let's see, we'd have negative 12 plus 3 is negative 9, that's true. We'd have 6 plus 8 is 14, that's true. Negative 12 plus negative 3 is negative 15, that's true. All three equations are made true by these values. And those are what I'll enter back in the assignment. Again, the parentheses and commas are already there, so just make sure you're putting things in the right order. The x value first, right? X was negative 2, the y value was second, positive 2, z value third, negative 1. Alright, now 2 of the 3 objectives are complete. We'll get back into that final one where they're just asking us, does this system have one solution, no solution, or infinitely many solutions? Alright. Okay, so let's start working on this. And remember, if it has one solution, then you're going to find it, just like the last example with negative 2 for x, 2 for y, 1 for z, negative 1 for z. If it has no solution, you'll eventually come across some statement like 0 equals 1 with no variables, right? Something that's clearly false. And if it has infinitely many solutions, you'll come across a statement like 0 equals 0 or 1 equals 1 with no variables, something that's always true. Alright, so I'm going to write this out and start working on it. Alright, so once again I have the system written out. All variables lined up nicely on one side, equals, and then the constants on the other. Equation 1, 2, and 3 from top to bottom. Alright, so this time every equation has all 3 variables. So what I'm going to do is I'm going to pick a variable to eliminate from 2 different pairs of equations. I'll do the y's this time. Alright, doesn't matter, you pick whatever you want when all 3 equations have all 3 variables. Alright, so I'm going to choose to eliminate y's. Alright, so first I'll do it from equations 1 and 3. That'd be really easy. So equation 1, we have 5x plus 4y minus 4z equals 44. Equation 3, you have negative 5x minus 4y plus 13z equals negative 75. And look what happens when I can add them right now, right? If I'm trying to eliminate y, the coefficients of y are already opposites, 4 and negative 4. Same thing for the x's, so both of those will be gone, and I'll have a negative 4z plus 13z, that'll be 9z equals, and then 44 plus negative 75, that'd be negative 31. right, negative 31. And then I try solving for z here. Z would be equal to, negative 31 ninths. Right? So if this has a solution, the value of z is going to be, negative 31 ninths. Okay, so let's do it again. So there I eliminated y from equations 1 and 3. Now let's do the same thing. Eliminate y from equations, I'll go 2 and 3 this time. Because again, that'll be pretty easy because those coefficients are already opposites for the y's. So equation 2 is, 5x plus 4y plus 5z equals 26. And equation 3 is negative 5x minus 4y plus 13z equals negative 75. And I can add the equations right now since I'm trying to eliminate y's and the coefficients of y's are opposites. Let's solve the x's, so those will both be gone, and I'm left with 18z equals, and then negative 75 plus 26. Right, that'd just be the opposite of 75 minus 26 would be 49. Right, so negative 49. Right, 26 minus 75. And then dividing by 18, we get z equals negative 49 18ths. Which, this is 2 times 9, this is 7 squared. These don't have any common factors, so that's as simple as it gets. Well, wait a minute. How can z be this value if it has a solution, but also this value, right? If I do a substitution, if I substitute this value, negative 31 ninths, for z over here, then we'll have the statement negative 31 ninths is equal to negative 49 18ths, which is false, right? If you can remember, if you're going through a system, solving a system, or solving in any equation with variables, if you can set up a way, if you eventually end up with a statement with no variables that is always false, right? Because if you got a common denominator, this would be negative 62 18ths, which is not the same as negative 49 18ths. This is false. This is bad. And if you end up with a statement like that, you end up with a statement that's false with no variables in it, that means that this system has no solution. Right? There is no ordered triple. There's no value of x, y, and z that will make all three equations true at the same time. But yeah, if you ever end up with a statement with no variables that is false like this, 0 equals 1, negative 31 ninths equals negative 49 18ths, something like that, that tells you the system has no solution. And a system with no solution has a special name as well. That's called an inconsistent system. So you may see that, right? That just means when they say a system is inconsistent, that just means the system has no solution, right? So back here of the options, I say, this system has no solution, no ordered triple that would make all three equations true at the same time. All right, now they may have done it a different way. Let me see. Yeah, see, they eliminated z's and then did eliminations, and you see they ended up with like 0 equals 52, right? A statement with no variables that was clearly false. No solution. All right, final question. I think this will be the final question. Same thing, right? We're given a system and asked, does this system have one solution, no solution, or infinitely many? And now we've seen examples of all three, right? We've seen examples that have had one solution. We've seen examples with no solution. That was the last example. We've seen some examples where there are infinitely many. So you should know what all scenarios are looking like now. Alright, so here's the system they gave us. Alright, now, once again, I'm noticing everything's lined up the way I like, right? All the x's and y's and z's are lined up on the left and equals, and then all the constants on the right. Great. Noticing that this third equation has just two variables, right? This third equation just has x and y in it. So I'm going to keep that third equation, and I want to make another equation with just x and y in it. And to do that, I would have to eliminate the z's from equations 1 and 2. Right? So that's what I'm going to do. I'm going to eliminate the z's from equations 1 and 2. Alright, so equation 1, you got negative x minus 4y minus z equals 7. Equation 2, negative 3x plus 4y, and then plus 5z equals negative 3. And to eliminate the z's, it's pretty simple. I would just multiply the top equation, both sides, every term, by 5. That'll give me negative 5z, and then there's positive 5z, right? Opposites for the coefficients of z. Alright, so after multiplying that top equation by 5, we get the following. We'd have negative 5x minus 20y minus 5z equals 35. And then the other equation would still be, I didn't do anything to it, would be negative 3x plus 4y plus 5z equals negative 3. And now I can add the equations together because the coefficients of z's are opposites and the z's will be gone. And that'll leave me with negative 8x minus 16y equals 32. And one thing I'm noticing here is that every single one of these coefficients is a multiple of 8. So I'm going to divide by 8. And then we'll have negative x minus 2y equals 4. And I'm going to call this equation 4. All right, E4. Now look, equation 3 that I kept earlier has x and y. Equation 4 has x and y. So equations 3 and 4 make a system of two equations with two variables that I can easily solve, right? So we have x plus 2y equals negative 4, and negative x minus 2y equals positive 4. And oh my goodness, look. If we add the equations the way they look right now, right? The coefficients of x are opposites, coefficients of y's are opposites, the constants are opposites. If I add the equations right now, we get 0 on the left, 0 on the right, and I get this statement with no variables that's always true, right? 0 equals 0 is a true statement, and it doesn't have variables in it, right? And remember we've seen this earlier in the video. It was a while back, but you're trying to solve a system, you're trying to solve an equation. If you ever end up with a statement with no variables that is always true, that means that that system or that equation, whatever you're looking at, has infinitely many solutions, right? So the system has infinitely many solutions. And we're not going to worry about finding any specific ones, okay? And they would call this system a consistent system with dependent equations, or just a dependent system if you want to write that too. But that's not what they're asking us to do here, just infinitely many solutions for this system. Wonderful. Alright, and that's it for this version of this assignment. Alright, again, I've said this at the top of the video, right? The questions you saw me doing in this version of the assignment, won't necessarily be the same questions you do when you do the assignment on your own. But, the types of questions, the objectives, the way I'm doing the problems, right? All that stuff will be the same as, what you're going to see, what you're going to do when you do it by yourself, right? And I hope watching me go through this helps you, when you're working on it on your own as well. And thank you for watching.